This is the demo for our AIG 130 course, Project 2. In this project, we took an existing machine learning solution and turned it into a Dockerized pipeline. Our goal was to create a portable and reproducible environment, so that the model runs the same way on any machine with Docker installed. In this demo, we will show the original machine learning pipeline, how we refactored it into a Python script, how we built the Docker image, and finally how we pushed it to Docker Hub and ran it on another machine.
This machine learning pipeline comes from a previous project where we predicted bike rental demand using the bike sharing dataset. In the original notebook, we loaded the bikeshare.csv dataset, performed pre-processing, and trained a regression model. The target variable is count, which represents the total number of bike rentals. We also did feature engineering and added some new features to improve the model's performance. At the same time, we dropped columns such as datetime, casual, and registered to avoid data leakage. The model used in the original project was a linear regression model, and it was evaluated using metrics such as mean squared error, root mean squared error, and R-squared. In the original notebook, there were also additional sections such as exploratory data analysis, EDA, and visualization, where we created plots and examined relationships in the dataset. These parts were useful during development, but they are not required for the containerized version of the project. EDA and visualization are interactive steps that are usually done only once to understand the data. They also rely on tools like Jupyter Notebook and Graphical Output, which are not practical or necessary inside a Docker container whose goal is to run the final pipeline automatically. So for the Dockerized version, we removed these sections and kept only the essential pre-processing and model training code. However, the original notebook runs only in a specific environment, and it is not ideal as a direct entry point for Docker. So the first step for containerization was to refactor the notebook into a clean and reproducible Python script. In this file, we moved the core logic from the notebook into a single, reproducible script. The script has three main parts: loading the data, building the pipeline, and training and evaluating the model. The load_data function tries to load the dataset from a local CSV file in the data folder. If the local file is not found, it falls back to the original GitHub URL of the bike sharing dataset. The build_pipeline function converts the datetime column, drops datetime, casual, and registered, and then separates the features and the target. It defines which columns are numeric and which ones are categorical, and then it builds a column transformer that standardizes numeric features and one-hot encodes categorical features. The final model in the pipeline is a linear regression model. The train_n_evaluate function performs a train test split, fits the pipeline on the training data, and prints out the MSE, RMSE, and R-squared scores. Finally, the main function ties everything together and runs the full pipeline. This script can be executed with Python src/main.py, and it produces the same metrics as the original notebook, but in a way that is easier to containerize. Here you can see the project structure that we created for containerization. At the top level, we have the root folder AIG130_project2_Docker. Inside this folder, there is a source directory that contains the main Python script, a data directory for the dataset, a notebooks directory for the original notebook, and also the requirements.txt file and the Docker file. Now, let's look at the main.py script inside the source folder. To manage dependencies, we created a requirements.txt file. In this file, we listed the main Python libraries that our pipeline needs, such as pandas, numpy, scikit-learn, matplotlib, and seaborn. Docker will use this file to install the correct versions of these libraries inside the container, which helps us avoid environment and dependency issues. Next, this is our Docker file, which is the core of the containerization step. We start from the base image Python 3.11 Slim, which is a lightweight CPU-based Python environment. This is sufficient for a classical scikit-learn regression model, and it keeps the image smaller and faster to build compared to heavy GPU images. Then we set the working directory to /app inside the container. We copy the requirements.txt file and run pip install our requirements.txt to install the Python dependencies. After that, we copy the rest of the project files into the container. Finally, we define the default command. When the container starts, it will automatically execute python src/main.py. This means that running the container will directly run the full machine learning pipeline. Now we will show how the pipeline runs locally, and then how it runs inside Docker. First, we execute the script directly with Python by running python src/main.py. As you can see, the script loads the dataset, prints the number of training and validation samples, and shows the evaluation metrics MSE, RMSE, and R². Next, we build the Docker image using the command docker build taig130ml. This command reads the Docker file, installs the dependencies, copies the project files, and creates a new image called aig130ml. After the build is successful, we can run the container with docker run rm aig130ml. Inside the container, the exact same pipeline runs, and we get the same evaluation metrics as before. This confirms that our environment is correctly encapsulated in the Docker image, and that the behavior is reproducible. After building and testing the Docker image locally, the next step was to upload it to Docker Hub so that other group members can access and use the same environment. First, we logged into Docker Hub from the terminal using Docker login. Then we tagged our local image with our Docker Hub username, using the command docker tag aig130ml scientity/aig130ml latest. This tells Docker that we want to publish our local image under the name scientity/aig130ml. Finally, we used the following command to upload the image to Docker Hub. Docker push scientity/aig130ml latest. This command pushes all the image layers to our online repository so that the image becomes publicly available. After the push is completed, the image becomes visible inside our Docker Hub account under the repository scientity/aig130ml. Anyone can visit our Docker Hub page and see that this image is now stored and ready to be used. This essentially means that our machine learning pipeline is no longer tied to my local machine. It is now hosted online and available to the rest of the group, or to anyone who needs to reproduce the results. Once the image is uploaded, each group member can run the exact same pipeline on their own computer without installing Python or any of the libraries manually. All they need is Docker Desktop. To download the image, they simply run docker pull scientity/aig130ml latest. And once the image finishes downloading, they can run the pipeline with docker run rm scientity/aig130ml latest. This ensures that everyone in the group gets the same results, using the same environment, with zero setup. This is one of the biggest advantages of using Docker for machine learning projects. In this part of the demo, we also wanted to show that the Docker image works on Linux. Here we are running the same commands on an Ubuntu machine. First, we check that Docker is installed by running Docker version. Then we pull the image from Docker Hub using docker pull scientity/aig130ml latest. This downloads exactly the same container that I used on my Windows system. Finally, we run the pipeline with docker run rm scientity/aig130ml latest. As you can see in the terminal, the container loads the dataset, trains the linear regression model, and prints the evaluation metrics, just like before. The important point is that we did not have to install Python or any libraries on this Ubuntu machine. Everything is already packaged inside the Docker image. This shows that the project is truly portable and reproducible across different operating systems. In the last part of the demo, we want to simulate two different situations on our system. One where Python is installed and the script runs locally. And one where Python is not available and only the Docker container can run the pipeline. First, we check whether Python is installed on this machine by running Python version. As we can see, the command returns a valid Python version. This means Python is currently installed and available on our system path. Because Python is available, we can run the script directly from our local environment using Python src/main.py. The script runs successfully. It loads the dataset, trains the linear regression model, and prints the evaluation metrics such as MSE, RMSE, and R². At this point, everything is still running locally, without using Docker. Now we will simulate a situation where Python is not installed on this machine. To do this, we rename the folder where Python is installed, so that Windows can no longer find the Python executable. After changing the folder name, we run Python version again. This time, the system shows an error saying that Python is not recognized as a command. This simulates a machine where Python is not available, or where the environment is not configured. Next, we try to run the same script again with Python src/main.py. As expected, this also fails, because there is no Python interpreter available on the host system anymore. The local environment is no longer able to execute the machine learning pipeline. However, even in this situation, we can still run the project using Docker. Instead of calling Python directly, we now run the container with Docker run rm scientity/aig130ml latest. Docker starts the container, uses the Python environment inside the image, and runs src/main.py from there. Once again, the dataset is loaded, the model is trained, and the evaluation metrics are printed, even though the host system itself does not have Python installed. This clearly demonstrates the main idea of containerization. The application and its runtime environment are packaged together inside the Docker image. So the machine learning pipeline can run reliably, even when the host machine does not have Python or any of the required libraries installed. To conclude this demo, containerizing the machine learning pipeline with Docker provided several important advantages. First, Docker gives us reproducibility. The same code with the same dependencies runs exactly the same way on any machine, whether it is mine or a group member's laptop. This eliminates environment issues and the common "it works on my machine" problem. Second, Docker provides portability. Our entire machine learning pipeline is packaged inside a single image, which can be pulled and executed anywhere with just a couple of commands. There is no need to install Python, libraries, or configure any environment. Third, Docker improves collaboration. Instead of everyone setting up the project on their own computer, the pipeline can be shared through Docker Hub, and each group member can reproduce the results instantly. And finally, Docker creates isolation, meaning the project does not interfere with other Python projects or system packages on the host machine. Everything runs in a clean, controlled container. Overall, Docker makes machine learning projects easier to share, easier to reproduce, and easier to maintain, which is why containerization is such an important part of modern ML workflows.